Great. I think we're going to get started with our next talk. So unfortunately, our next speaker wasn't able to join us in person today. But our next speaker is Kathleen Wendt. She very nicely recorded a talk that we will be watching, and then she's going to join virtually to answer questions at the end. So Kathleen is an assistant professor at Oregon State University. A lot of her work focuses on, has ranged from the tropics to the poles, and she's an expert in uranium series disequilibrium dating, has been specializing to improve these methods for years now. And today her talk will be an overview of uranium series dating. So her video will appear up here.
Okay, hi everyone. My name is Kathleen Wendt. I am an assistant professor, senior researcher here at Oregon State University, and I am so very sorry I couldn't be with you there in person. I had no idea that the start date of this new position was going to align so closely with S4, so unfortunately I have to give this presentation virtually, but I hope it won't be too disappointing. I tried to make it as entertaining as possible. I'm going to be giving a very broad overview of the theory behind uranium-thorium dating, and then Juan is going to take in after me and dive into the details of the uranium-thorium dating equation. All right, we have a lot to get through, and I just want to acknowledge that those of you sitting in the audience, you probably have a mix of familiarity on this topic. Some of you may be first-year PhD students learning about uranium-thorium dating for the first time. Others already have experience in it. Maybe you've already produced some AGEs of your own. So this talk is going to be brand new information for some people and a review for others, but hopefully it will be interesting nonetheless. So let's start at the very beginning, and at the very beginning is the periodic table. So we're looking at uranium and thorium. They are both heavy elements that are part of the actinide series, and they are both radioactive, meaning that they will spontaneously decay and become different elements over time. So let's look at the three main naturally occurring uranium isotopes. The first being uranium-238, which has a whopping abundance of 99%. I'm just going to move myself over here. Uranium-238 has a half-life of about 4.5 billion years, which is roughly the age of our Earth. It decays through a series of intermediate daughters, making its way all the way down through the decay chain to lead-206, which is stable. The second most abundant uranium isotope is uranium-235. It also has a very long half-life of 700 million years, and it also decays through its own decay chain through a series of intermediate daughters, making its way all the way down to lead-207. Now, if you're working in the energy sector, you may be most interested in uranium-235 because the nucleus of uranium-235 can undergo fission, which is the basis of nuclear energy. So uranium-235 is the one that tends to get most of the attention, but we as geochemists are actually most interested in uranium-238 because it is the ratio of parent uranium-238 to daughter thorium-230, which is the basis of uranium-thorium dating. So this talk is going to be focusing on uranium-thorium dating, but I will briefly mention uranium-uranium dating, which is based off of the disequilibria between 234 and 238. We'll also touch on uranium-protactinium dating, which is the decay of protactinium-231 from uranium-235. And then we'll briefly touch on uranium-lead dating, which involves both decay chains. All right, so if you were to go outside and find a rock, and that rock had a little bit of uranium in it, and that uranium was in secular equilibrium with its intermediate daughters, then theoretically you would find all of the elements on both of these chains in your rock. So I mentioned the word secular equilibrium. Let's take a second and define it to make sure that we're all on the same page. I'm just going to minimize myself a little bit here. Secular equilibrium is a situation in which the quantity of radioactive isotopes remains constant because the production rate of a nuclide is equal to its decay rate. And this is a very special situation that can only happen if a parent isotope has a much longer half-life than any of its intermediate daughters. We can express secular equilibrium mathematically using activities. So activities are simply the number of disintegrations per second, or the decay rate, with n representing the number of atoms in nuclide 1 and lambda representing the decay constant of nuclide 1. So in secular equilibrium, all of these activities, all of these decay rates are equal to one another. And likewise, if you were to divide one activity from another activity, you would result in 1 because they are, again, equal to one another. So secular equilibrium is one of these things that's sort of funny or difficult sometimes to conceptualize. So when I teach about it, I like to show this cartoon. So you can imagine having a massive tanker truck that is full of water, and this tanker truck has a tiny little leak in it. So this leak leaks out drops of water that fall into a secondary container, shown here by this bucket, which also has a leak in it. So water leaks out into this cup, which also has a small hole in it. So water leaks out, and so on and so forth. At secular equilibrium, the water levels in each of these containers remains constant because the rate of water entering a particular container equals the rate of water leaving that container. All right, so now we can put our sort of U-series systematics onto this cartoon. Uranium-238, again, this is this one with a 99% abundance. It's got a massive half-life of 4.5 billion years. Uranium-238 actually decays to 2 different intermediate daughters with very short half-lives. This is thorium-234 and protactinium-234. Because they have such short half-lives, we often disregard them when we are talking about carbonate dating because they are such short half-lives that they're sort of irrelevant to the timescales we are working with. So we will assume or pretend that uranium-238 decays to uranium-234, which has a half-life of 245,000 years. This alpha decays to thorium-230, which has a half-life of 75,000 years. Now let's imagine that I reach in and I take that thorium-230 cup and I dump out all of the contents in it. So when I put it upright again, what happens is that because the cup is empty, the rate of drops coming into the cup will not equal the rates of drops coming out of that cup, right? So in other words, the activities of this system are no longer equal. This system is in disequilibrium. And the reason why it's so important to understand what disequilibrium is because it is the basis of uranium-thorium dating. So uranium-thorium dating is part of the U-series disequilibrium family. There are multiple chronometers that are part of U-series disequilibrium. Uranium-thorium is just one of them. But the basis behind all disequilibrium dating techniques are as follows. So if we kind of illustrate this using a graph, we can see on the x-axis we have time moving forward towards the right, and then on the y-axis we have the daughter-to-parent activity ratios. So at time 0, our daughter-to-parent, our system, is in secular equilibrium, so the activity ratio here is 1. And this system will stay in secular equilibrium until it encounters some sort of chemical fractionation event. And this chemical fractionation will fractionate all of the daughter isotopes away from the parent isotope so that the daughter-to-parent isotope ratio is 0. Over time, the parent will continue to decay to the daughter isotope, so the daughter isotope will accumulate following this exponential saturation curve, eventually returning to secular equilibrium. So we can now apply this to our uranium-thorium dating schematic. We have a system here that is in secular equilibrium. Again, the daughter-to-parent ratio is 1. Then we knock over our thorium-230 cup, we basically lose all of our daughter. So now our daughter to parent activity ratio is at 0. And then over time, thorium-230 will continue to accumulate because uranium will continue to decay. And this accumulation will follow this exponential curve, eventually returning the system back to secular equilibrium. So the basis of disequilibrium dating is that we can go in and measure the daughter to parent ratio in order to determine the time that has passed since this chemical fractionation event, since the system was thrown into disequilibrium. So now let's take this theory and apply it to caves. What type of chemical fractionation event could be taking place in caves that would separate thorium from uranium? Let's take a look. Okay, so the chemical fractionation that occurs is thanks to the very different chemical properties of both uranium and thorium. So uranium and thorium are both actinides, as I mentioned, but they have very different valence states under oxidizing conditions, which is typically what we see in caves. Under these conditions, uranium is soluble, thorium is highly insoluble. So an example to sort of illustrate these solubility differences is that in our oceans, for example, uranium is about 5,000 times more abundant than thorium. So thorium really, really does not like to be in water. Coming back to caves, we can imagine that we have some rain raining down onto the surface of our cave. This rain infiltrates down through the soil column. Soil is chock full of microbes. Those microbes are respiring, so soil has a bunch of CO2 in it, and so that water picks up some CO2 as it infiltrates down. Now, when CO2 dissolves into water, it makes carbonic acid, so that water becomes a little bit acidic. And so if we zoom into this fracture here, once this water has reached our carbonate bedrock, I'm just going to move myself over. Because this water is rich in CO2, it's slightly acidic, it will begin to eat away at the bedrock on either side of this fracture, right? And this bedrock has a certain quantity of uranium as well as thorium, so that over time, this uranium and thorium are freed into this fracture. Now, uranium, as I mentioned, is soluble, so it happily goes into solution. Thorium, on the other hand, is highly insoluble. You can kind of think of thorium as being really, really sticky. So it's going to want to stick back to the walls of this fracture, right? So in the end, what you get is water that infiltrates its way down that theoretically only has uranium and no thorium. So this little droplet drops onto our stalagmite and it precipitates a fresh new layer of calcite that contains only uranium and no thorium. So this is our fractionation event that we were talking about previously. So now we allow some time to pass and the uranium that is in our little calcite layer will continue to decay to thorium. So that follows this simple exponential saturation curve shown here. Again, on the y-axis, we've got the activity ratio of daughter to parent. And then on the x-axis, we're looking at time, again, moving forward. And again, I'm in the way. Here, let me move myself. Okay, I think I accidentally stopped recording. All right, so let's pick up where we left off. We were envisioning a freshly precipitated layer of calcite, which contains only uranium and no thorium. So this is when our clock starts at 0, which is represented here on the graph. Over time, uranium will decay to thorium, and so the activity ratio moves along this exponential saturation curve until we reach 1, an activity ratio of 1, or secular equilibrium. Once we are at equilibrium, it's kind of like game over. We can't use uranium-thorium dating to determine the age of our speleothem. We would have to employ some other type of dating tool. So the question becomes, when does this system reach secular equilibrium, right? What is the limit of uranium-thorium dating? And to envision that, we can use our little thorium-230 cup. So here I've arbitrarily drawn a dashed orange line, which represents secular equilibrium. It would take 600,000 years for us to reach over 99% of the way to that secular equilibrium curve, right? This time period represents 8 half-lives of thorium-230. At this point, we've sort of reached our limit as far as instrumental precision goes. We've reached our limit of being able to distinguish between disequilibria and equilibria. So this is what we often refer to as really the absolute limit of uranium-thorium dating. Now let's look at the uranium-thorium dating equation. If you look at the first half of this equation, if you're a little mathematically inclined, you'll notice that it looks, a lot like this curve. So in the y-axis, we have the activity ratios, right, in that y place, and then we have this equation for this exponential curve. And then we have a bunch of other stuff, right? So where does this stuff come from? What is it representing? It turns out that nature is a lot more complicated than theory. And the complication that I'm referring to here is that in this decay series, uranium-234 is often in disequilibria with uranium-238, right? And so in order to get an accurate age, we have to account for this disequilibria. So before we go any further, let's take a break and talk about why it is that these uranium isotopes are in disequilibria. I'm gonna move myself again. All right, so if you were to take some water from a river or a lake or the ocean, groundwater, really any water on Earth's surface, and you were to measure the activity ratio of 234 to 238, you would find that it is likely in disequilibria, and that 234 is generally more enriched relative to 238. So why is that? The reason comes down to this process called alpha recoil. So we can go back to our little diagram and imagine that we've got uranium-238 in this bedrock here. Over time, uranium-238 will decay through alpha decay to thorium-234. Again, has a very short half-life. This moves on to protactinium-234 and eventually uranium-234. This initial alpha decay is a very energetic process, right? So what happens is an alpha particle basically gets shot out of the nucleus and the nucleus recoils as a result. So it's not too dissimilar to like shooting a gun where the alpha particle is the bullet and the recoil of the nucleus is like the recoil of the gun after it's shot. So this recoil damages the site that the nuclide is held in. And in the end, the daughter nuclide, which will eventually become 234, is loosely bound within the crystal lattice of its host mineral. And because it's so loosely bound, it is subject to preferential leaching, meaning that because it's not tightly held within this crystal lattice anymore, it can easily be sort of leached away into solution. As a result, the activity ratios of most fresh waters as well as seawater, the activity ratio is greater than 1. And I'll also mention briefly that when we talk about uranium activity ratios, we often write it in delta notation. So that is simply delta 234 uranium, which equals the activity ratio minus 1 times 1,000. And so if the system is in equilibria, this activity ratio would be 1, and your delta 234 uranium would be 0. But anything above 0 is representative of some sort of disequilibria. Okay, so coming back to our graph, this first curve that we started out with is representative of a system where 234 to 238 are in equilibria. So the initial delta 234 is 0. So this curve really only follows this part of the equation. But as I mentioned in nature, this is typically not the case. Speleothem delta 234 initial ratios are usually between 0 to 1,000. And so this part of our age equation basically makes up for that. So here's an example of how the curve is sort of augmented given the initial delta 234 ratio of 1,000. So there are a number of different ways to sort of graphically illustrate the uranium-thorium dating equation. This is just one that I usually start out with when introducing this topic, but I want to show you guys just one more, and I'll have to move myself to do that. So this is called the Edwards diagram because it was popularized by Larry Edwards back in the 80s. And again, we're dealing with very simple, very similar axes as we were in this first diagram. They're just sort of in different places. So now we have the activity ratio of daughter to parent on the bottom. The age in thousands of years are these sort of lean dashed lines shown here. And then instead of looking at initial ratios, we're looking at the measured delta 234, which is actually one of the variables that's plugged into this equation. So you could take a lot of time staring at this diagram. It's quite mesmerizing, but I'll just mention briefly as an example, say you go into the lab and you measure your delta 234 to be about 100 in your sample. And then you measure your 230 to 238 activity ratio, which turns out to be about 0.6. You can use this graph to basically work out, so 100 and 0.6, work out that the age of your speleothem is about just shy of 100,000 years before present. Again, also notice that the delta 234 are all making their way to secular equilibrium, which is represented here at, again, about 650,000 years before present. Okay, so I highly recommend taking some time to really look at the dating equation, look at this graph, kind of play around with the different type of variables that are part of this dating equation before you head into a lab, which will likely use maybe Excel or Python to sort of spit out ages for you. It's really, I think, a fun exercise to understand the theory and the math behind what it is that we're working with. Okay, so the dating equation does come with some caveats, as always, right? So one of the caveats is that this equation will only work if your sample remains closed throughout its lifetime. A closed system means that there is no addition or loss of either uranium or thorium throughout the lifetime of your speleothem. So there's really no good way to tell whether or not your speleothem is open or closed, as an open or closed system based off of just looking at it. You usually have to do a little bit of chemistry to find out. But one sort of trick of the trade is to look at the density of calcite. So if you've got a speleothem that has very dense, well-laminated speleothem growth or layer growth, it's likely that that particular part of your speleothem will be a closed system. When you find a speleothem that has very porous calcite that grew really rapidly, probably through some very fast, splashy drip waters, this porous calcite is usually, crumbly to the touch. More often than not, porous calcite tends to be an open system, so you won't be able to get reliable ages from this particular material. It's not a guaranteed test, but it's something to look out for before you start drilling. Another requirement, very important requirement, is that the equation assumes that there is no initial thorium. If there is initial thorium, especially initial thorium-230, we need to correct for it. Okay, so the first question is how does thorium make its way into our sample? And so it can do so in a number of different ways. So for example, if you go back to our diagram where we've got this water moving through a fracture, this water often contains some particles or colloids that thorium, being so sticky, will like to stick to. And so you can imagine these particles like tiny little transport vehicles that bring thorium down through these fractures and then eventually are deposited on our speleothem. And again, what we're looking here is at we want to be able to distinguish the thorium-230, which has decayed from the uranium in the calcite layer of our speleothem, versus the thorium-230, which was sourced from some sort of detrital material. And that would be acting as kind of contamination to our sample, and that would bias our ages too old if we can't adequately correct for them, for that initial value. Okay, so again, one way that thorium is incorporated into our speleothem is through this sort of tiny vehicle transport mechanism of particles and colloids coming in through the drip waters and the ceiling of our cave. Another mechanism is kind of based on the fact that caves are really dirty. If you've ever been in one, you might know. So you can imagine that dust can be blown in from the entrance of a cave and settle onto a growing speleothem. Caves flood sometimes. There's often sediment transport. Animals will kick up dust within our caves. And all of this detrital material can kind of cement itself onto a growing speleothem. In fact, I think it would be safe to say that throughout your career, you will not find a speleothem that doesn't have some sort of initial thorium component that you need to correct for. Luckily for us, though, we can constrain that initial 230 thorium component by measuring 232 thorium. All right, so both 230 thorium and 232 are thorium, so they both have the same chemical properties and they behave the same in these sort of low temperature oxidizing environments that we often find in caves. The key difference between these two thorium isotopes is that they are both on different decay chains, right? So 232 thorium is the start of its own decay chain. It is not the daughter of 238. And this is really important because if we know the initial ratio of 230 thorium to 232 thorium, and we can measure the concentration of 232 thorium, then we can calculate for the amount of detritally sourced or contamination that is from our thorium-230. So again, I'll reword that because it's very important and I hope I'm making it clear. If the 232 thorium concentration is known and we know the initial ratio, then we can calculate the initial 230 thorium concentration, again using 232 thorium as sort of a proxy to calculate the amount of initial contamination in our sample. All right. How do we constrain, or how do we know our initial 230 to 232 value? It turns out that there are a number of different methods to get at that ratio. I could spend probably an entire hour talking about initial 230 thorium corrections. I'll just summarize by saying that there is no correct method here. It really depends on your sample. So I'm going to just briefly talk about each of these methods, and then it'll be up to you to do a little bit more reading and research to decide which method you will use for your particular sample. Okay, so method one, for example, just uses the bulk earth ratio of 230 to 232. This is usually the most common way to do things, and it's pretty appropriate when we're working with speleothems that have a relatively low detrital component. Method two is a little bit more sophisticated from method one because you're using initial ratios that are commonly found in speleothems as opposed to simply using bulk earth ratios. Method three and method four are ways to sort of directly measure this ratio from your sample. So as an example, Wang et al. 2001, published I think in Nature, was a very famous paper. It was one of the first Asian monsoon papers. It's the the publication of the hula record, the first hula record. If you dig into their supplementary information, you'll find that what the authors did is they found several detrital-rich lamina in their speleothem. They dated above and below that lamina, and so that they were able to constrain the age of that lamina. And then they measured the 230 to 232 ratio of that detrital material, that detrital-rich lamina. And because they knew the age of the lamina, they could basically calculate the initial ratio. So again, I highly recommend if you're reading a speleothem paper to really dig into those supplementary information notes to see which type of method the authors used and why. Okay, method 5.2 involves a little cave monitoring, so you're looking at soil leachates and cave sediments in order to, again, better constrain the initial ratio of your source material, that detrital material. Alrighty. Let's take a break now from systematics and talk a little bit about the history of uranium thorium dating, which I always find to be really interesting. So starting at the very beginning, Henry Becquerel in 1890s, he had the bright idea to take a bunch of uranium salts and put them on a photographic plate. He then put this plate into his desk drawer, which is dark, and left it there for some time. When he returned and developed that plate, he noticed that the uranium salts darkened his photographic plate. Now, whether or not he did that on purpose, kind of left his uranium salts on a plate on purpose, or if he did it on accident, that's a bit debated, but nonetheless, it was a really interesting discovery. Shortly after, Marie Curie, who hopefully you guys have heard of, demonstrated that uranium and thorium compounds could ionize air. So this was sort of a time when there was a lot of discoveries about this new phenomenon known as radioactivity. In 1902, Rutherford and Soddy developed the equation of radioactivity that about a decade later, William Urey could measure uranium concentrations in a carbonate material. My understanding is that, at least the earliest paper I could find of an example of uranium thorium dating goes back to Barnes et al. 1956, where they applied uranium thorium dating to corals. But it took about a decade later before people started to catch on to this idea of 234 to 238 disequilibrium, which is what we talked about before. So in 1965, Wally Broecker and his colleague Kaufman were able to calculate the uranium thorium equation that we still use today. So in the 1970s, alpha spectrometry was routinely used to date speleothems. This is a very tedious process where you measure the concentration of uranium in your sample, and then you basically count the number of alpha decays that take place over a long period of time. You need a lot of speleothem to do this, something like 30 grams. And it, again, takes a lot of time, and the age uncertainties aren't so great. So we were sort of stuck in this space for a while, until about 1980, when Jerry Wasserberg, who is a famous geochemist at Caltech, hired 2 PhD students to make the first mass spectromic measurements of uranium-234 and thorium-230. So that was Chen, who published in 1986 the measurement of uranium-234. And then this guy, who might look familiar to many of you, this is a very young Larry Edwards, who published his findings of measuring thorium-230 using mass spectrometry in 1987. So this was all done on the TIMS, the thermal ionization mass spectrometer. Since then, there's been additional technological developments using an ICP-MS, and so on and so forth, all the way to 2013, when Larry Edwards and Hai Cheng developed the Faraday cup measurement technique, which they used to further constrain the half-lives of uranium-234 and thorium-230. And this is a picture of Hai Cheng, by the way, if you haven't met him. I really like this picture. I think it came from like a local newspaper or something. But he's holding up a speleothem, and he's showing these drill holes for uranium-thorium dating, which are very, very small relative to, alpha counting back in the 1970s. Again, we were working with 30-gram chunks of calcite, and now we're down to tens of milligrams of calcite. So really spectacular reduction in sample size, kind of as a result of these advancements in technology. So a little bit more about these technical improvements and how they have allowed us to really decrease the uncertainty of our ages as well as extend the limit of uranium thorium dating. So in pink we have alpha spectrometry, this is alpha counting. In yellow is TIMS, so this is the thermal ionization mass spectrometry that was developed in the late 1880s. And then ICP-MS, which today is state of the art, and it has allowed us to not only decrease our 2 sigma uncertainties, but also extend that uranium thorium dating limit that we were talking about earlier to about 650,000 years. All right, so what does all of these technical advancements result in? They result in very, very precise ages. So here is an example of a very exceptionally dated speleothem that grew in China over termination 2. You can see the ages here and then the 2 sigma uncertainties, which are represented by these little bars. So to give you context, here at OSU, I did a postdoc in ice cores. I was measuring CO2 concentrations in ice cores. And over termination 2, we would be lucky if we got maybe 2% relative uncertainty in our ice core chronologies. What we're looking at here during termination 2 using speleothems is sub-per-mil precision. So it's really exceptional. It's no small thing that we kind of refer to speleothems as the timekeepers of the paleoclimate community. There is no other paleoclimate archive that can rival this precision at these time scales. So with great power comes great responsibility, right? Just because you can date something very, very precisely doesn't mean you have to start dating the heck out of your speleothem. You need to have a very good sampling plan. And this is something that Juan will talk to you more about in detail. So I won't talk about it at length. I'll just mention that there are a number of different ways to calculate the amount of powder that you need to get to a particular precision. So your precision is dependent upon counting statistics. How much sample you'll need will also depend on the ionization efficiency of your mass spectrometer, so basically the efficiency at which your mass spec can ionize your sample. Once you have an idea of how much sample you will need per uranium thorium age, it's really a good idea to have a game plan. So to make a lot of diagrams, make a lot of pictures, draw maps, so that when you do drill your uranium thorium ages, you are avoiding, for example, growth discontinuities or hiatuses, which could incorporate a lot of that detrital 230 thorium, which involves a huge correction and could lead to large uncertainties. You also want to avoid any type of post-crystallization disturbances or fluid inclusions, which the authors of this paper show very nicely here in yellow. You also kind of want to have an idea of how much time your speleothem spans, so you have an idea of how many uranium thorium ages you'll need to build an accurate chronology that is at the resolution that you're trying to get at. Again, Juan will talk about all of this. I just also want to briefly mention that another aspect of determining your sample size, you also need to keep in mind your sampling uncertainty. So that's shown here. This is an example of a fake stalagmite called stalagmite X. I took this example really from Dirk Hoffman, who gave an excellent talk about uranium thorium dating at the last S4 speleothem summer school. So in this example, he shows 2 drill holes, which are shown here in red. So with this drill hole here, this subsample, he drilled 2.5 grams of powder, which is what you would need to get sub-per-mil precision, right? And that's great news. So you've got really great analytical precision, but because you've drilled such a massive hole, you've incorporated over 2,000 years of 2,000 growth layers, right? So your sampling uncertainty is much larger than your analytical uncertainty. Example number 2, you drill a little less powder, about 25 milligrams. You get larger analytical uncertainties, sure, but they are equal to your sampling uncertainties, right? So you want to really be careful about this, because even if you've got these really excellent ages with this very high precision, you're going to need to go back and increase the total uncertainty of your ages if your sampling uncertainty ends up being larger than your analytical uncertainty. All right, so now let's pretend that you've got your ages, you've got your powder, you've drilled it up, you're ready to go into do some chemistry. So to do that, you need to go to a clean lab. There are a number of different examples of clean labs around the world. Here's the one at Oregon State University, which right now processes a lot of seawater samples, but I'm hoping to start up U-series dating applications in the near future. Then you got to get started on chemistry. So uranium thorium dating chemistry takes about 3 days to get a sample set of about maybe 10 samples at a time through chemistry. It involves using very, very clean acids, right? So here's an example of a distiller that we have at Oregon State University to make sure that we're redistilling our acids so that they are as clean as possible. We digest our samples, we spike them using uranium and thorium isotopes that are not, they are man-made, so they are not natural isotopes, so they will not be in our samples. So we use a spike, and we essentially load our sample onto a column. So this is sort of where the magic happens. Uranium thorium chemistry really depends on ion chromatography. You essentially load your sample into this ion exchange column that has this ion exchange resin, and then you can basically take a uranium aliquot and a thorium aliquot separately. Once those are separate, you can measure them separately on a mass spectrometer, and then you get your ages. So here's an example of a results table that you would typically get after you've measured your samples on a mass spectrometer. Most people go straight to the end looking at the ages of your results, since that's sort of why we're here, is to find out the age of your speleothems. But I just want to briefly point out that there's a lot of really good information in these tables, so don't just gloss over them. Make sure you take some time and understand what each of these columns mean. So for example, in some studies, people will look at the delta 234 initial and use it as a proxy for whether or not the environment that your speleothem is growing in is in either a wet or a dry environment. This is very applicable to maybe deserts that experience drastically different conditions during glacial periods, for example. Another column that can be quite important is thorium-232. So thorium-232 is again a proxy for this detrital material, so sometimes people can use it as sort of a proxy for dustiness. If you've got a speleothem that's at the entrance of your cave and you've got a lot of dust flying into the cave and maybe you get this spike of 230 thorium, you could potentially be using this as sort of like a way to reconstruct dustiness over time. So there's just a lot of information really that could be derived from this table. Make sure to take a close look at each of these columns and understand what each of them mean and whether or not there's any other kind of additional paleoclimate information that you can extract from them. Okay, so that's uranium thorium in a nutshell. Let's look very briefly at some other chronometers that are part of the U-series disequilibrium dating family. So first up, we have uranium protactinium. Protactinium has very similar chemical properties to thorium. So the systematics between uranium and thorium are kind of analogous to uranium protactinium and vice versa. Uranium protactinium is based off of the decay of uranium-235 to protactinium-231. You can use it to date carbonates between 10 and 250,000 years. The sort of power in uranium protactinium dating is that uranium protactinium dating is based off of a separate decay chain than uranium thorium dating. So you can essentially use it as sort of an independent check for your uranium-thorium ages. Then we have uranium-uranium dating. This is based off of the disequilibrium of 234 and 238, which we talked about before. You could theoretically use this disequilibrium ratio as a way to date your speleothems, again, solving just for T. And again, theoretically, this can be used to date speleothems up to 1 million years. There are a lot of challenges, though, that come with uranium-uranium dating, the biggest of which is constraining this initial activity ratio. So the 234 to 238 activity ratio tends to vary greatly in space, right? So different source waters will have different activity ratios. It also varies through time. So you may see activity ratios that change through time in your samples. So estimating the initial activity ratio is very difficult to do, and you end up, usually if you were to apply uranium-uranium dating, you would end up with age uncertainties that are orders of magnitude, larger than uranium-thorium dating. So it's not really, considered that helpful, but if you have very special circumstances where you really understand the delta 234 of your source water and how it varies over time, you can theoretically use uranium-uranium dating to date carbonate samples that are just beyond that 650,000 year limit for uranium-thorium dating. And so that's what Lee et al. Did in 2001, so definitely check out that paper if you're interested in learning more. Okay. Then we have the uranium-lead chronometer. This is the last one that I will talk about. Uranium-lead allows us to date speleothems that are older than 1 million years. It is based off of the two decay chains that we've been talking about, 238, which leads us all the way to 206 lead, and 235, which leads us to 207 lead. Here are the two dating equations. They are normalized by common lead, 204, which is non-radiogenic. You can basically take these two equations and build an isochron, which is shown here. And then essentially these two equations can then be placed into an inverse Concordia diagram to calculate an age, as well as get a better handle on your initial conditions. So I don't have a lot of time to go into detail about uranium-lead dating. I highly recommend checking out John Woodhead's paper, which he published in 2012, which is a really good read, very comprehensive. I would also recommend checking out Imani's lecture of uranium-lead dating that he gave at the last speleothem school. It's 40 minutes long, so he obviously goes into a lot more detail about sample prep, about initial conditions, about Concordia diagrams, all that good stuff. So it's on YouTube and available to watch. So make sure to take a look at that if you're interested in learning more about uranium-lead. All right, so that's all I have. I just wanted to also say before I leave, thank you to the organizers for inviting me. It's really a huge honor being an early career scientist and getting to talk to all of you at a summer school like this. I actually was at S4, the very first S4 in 2014, I think it was. It was held at Oxford, so it's been really cool to be able to return now as an expert and talk about uranium-thorium dating. I am also around for questions, and so please feel free to ask them. If I can't answer them or if we run out of time, definitely ask Juan. Highway's also there, a few other people who know quite a bit about uranium-thorium dating, so they can help answer your questions. So with that, thank you for your attention, and I hope to see all of you guys in person very soon.
That was a great talk. I think now Kathleen is with us live. I don't know if she's available. Oh, there she is.
Hi guys.
So if you have any questions, please raise your hand and Kathleen will answer them.
I also want to say that I just learned from Twitter that the first S4 was actually in Heidelberg, Germany. I went to, I guess, the second S4. I thought I was at the first, but I went to the one in Oxford, which I think was in 2015. So, oh, hi, Valdir. I see you in the back. Hi, Leah. Familiar faces. Hi, guys. Again, I'm happy to answer questions. If we run out of time, or if I can't answer a question, which might be the case, I can defer to Juan or many other experts in the room right now who know a lot about uranium thorium. I think I see Highway. Hi, Highway. Good to see you.
Okay, yeah, we have a question in the back from Andrea. Can you hear him?
I can't. Maybe you can
Okay,
repeat
maybe-
the question after he's done asking.
Or Andrea, do you want to come to the front where the microphones are?
Hi, Andreas. I don't think we've met in person, but I know of you.
Yeah. So my question is about uranium leaching in dating.
Yeah.
So have you some experience or some tips for us in order to discriminate the potential leaking area in speleothems, or you just go for trial and error?
Right. So when we're talking about the leaching of uranium from speleothems, we're talking about whether or not your speleothem has remained a closed system over time. So if you have a loss of uranium, your system is no longer closed. The question was, how do you test for that? There's no really good way to test for that other than dating your sample and seeing whether or not your ages are in stratigraphic order. You can take a look too at the uranium isotope ratios to give you a little bit of a hint about whether or not you're losing uranium over time. But unfortunately, there's no kind of magic way to get at that in sort of a single step. You have to do a little bit of problem solving. And again, the fastest way, so in my experience, when I've encountered open systems, I've ran a few different dates and they're just not in stratigraphic order. So then I move to another speleothem in that particular area to try and replicate that particular speleothem. And if I can't get a replication, so I can't replicate those ages, then I'm probably dealing with an open system. So it's then no longer trustworthy. I can't really trust those ages. Can I see a show of hands of the room? Who has measured uranium thorium ages before? Okay, great. I didn't know if the whole room would raise their hand, and I was just giving a super basic overview to everyone. Okay, that's good.
And I think
So there's some new students in the audience. Yeah.
And I think we have another question. Do you want to?
Yeah. Okay. Go ahead.
Ask it?
Hello. So I see that you talked about the problem when we have an initial thorium, so we have a high amount of thorium. But what about if we have a really low amount of thorium? How can we deal with that? Actually, I'm really new with dating, so I don't know if it is a good question or not. So.
Yeah, no, it's a great question. So one example where we would have very low thorium. So there's two different things. So we've got our detrital components. So we've got initial thorium-230 coming in. That is sort of contamination. If you have a speleothem with really low detrital thorium, great news. That's awesome. Your correction will be really, really small, and it won't, influence your uncertainties too much. So that's really an ideal situation. And when you look at those papers from the Asian monsoon, those Chinese speleothems, that's really what they're working with. They're super, super what we call clean samples. If you're looking at low thorium that is radiogenic, so a daughter of uranium in your particular calcite sample, you're usually looking at a sample that is really, really young. So then it depends on the precision of your instruments to be able to measure that sample. If you're working with a super young sample, though, you might want to defer to other dating techniques like band counting. If you're, collecting a sample that is actively growing, you know that top layer is year 1, and then you can count backwards in time, and that would be a little bit more robust than uranium thorium ages, where you're sort of pushing the limit of that thorium detection.
Thank you.
Yeah.
I think we have time for one short question. Yeah.
Not short, maybe. Someone with a short question is a better idea then.
Anyone have a short question? All right, go for
Try
it.
and make a long question short.
Yeah, why don't you come up here so
Yeah,
she
I
hear.
can try to shout. Can
Or
you hear
shout.
me there?
I just barely, but you asked you to repeat. Go ahead.
I'm kind of stuck. I'll make my way. It's going to turn into a very long question this one. Hi, Hubert Vonhoff from Mainz.
Who is this that I'm talking to?
Hubert Vonhoff, I'm in Mainz. I have to do with dating, but I don't do the dating myself. But we have projects lately in which we use both, and this perhaps is a question to all the uranium thorium people, in which we use both laser ablation and solution-based dating, right? I know the basics of this, right? Laser ablation, we have less sensitivity, so we have not so good errors and things like that. But we can do a lot more. I was trying to provoke perhaps a little bit of a discussion here where we think the field is going. Are we moving towards laser and simply by being able to shoot so many more holes, get better statistics, get good dating? Or is there a limit to this that we really need solution-based always? That's maybe a question I have.
Excellent question, and I just have to say, I have the same question. Because
Very good.
I've never used laser ablation, I'm aware of it, but I'm not highly familiar with it. So if anybody in the audience has used both methods, please feel free to say what your experience is as far as especially the uncertainty levels between the two.
Basically, the answer to that it depends on how much uranium you have on the stalagmite and how much thorium. Because with laser ablation, your precision is highly constrained by counting statistics. Counting statistics is basically how much noise is from the thorium to 30 signal, which is also affected by the fact that you are introducing into the plasma the whole matrix. And that makes the signal inherently noisier than in solution mode. So I think that yes, we can get more edges, we can get probably higher resolution, but we are still far from achieving the precision that we can get on solution mode.
Can I have a follow-up on that? Because I'm talking to uranium. Do we need to stop?
I think we should move on.
We should
and take this conversation to lunch.
Yeah, that's fine.
Yeah, so let's thank Kathleen one more time. And I think we have a couple announcements about lunch. Bye. A couple announcements about lunch. You can either leave your things in the room or take them with you. We will be locking the door. And we're all gonna walk over together as a group. I think we're gonna meet outside the building, maybe in, like 5 minutes? 5 minutes. 5 minutes. And you're gonna receive a meal ticket as you walk into the restaurant, and that's what you'll present. Anything else? Let's do it. People, wait, one second.